All right, today we're going to talk about charge and current. But before we get into that, I just want to say I hope you guys are all doing well. I have been spending my time between teaching and grading, watching a lot of really bad TV, baking a lot of cookies, and let's see what else. Trying to teach myself how to cross stitch, and I've thought about trying to learn how to yodel. No, I'm just kidding. But anyway, okay, let's talk about charge. So when we talk about charge, we first have to do a really quick review of matter, and this should all just roll right off. So matter is anything that has mass and takes up space. We know that all matter is made of atoms. We know that an atom is the simplest form of matter, or at least I hope we know this. It's made of protons, which have a positive charge, and neutrons that have a neutral charge, and electrons that have a negative charge. So we know that the protons and the neutrons form up the nucleus, and the electrons are kind of traveling around in sort of a cloud outside of the atom. We know that the protons and the neutrons are held together by the strong nuclear force, and that typically the protons and the electrons equal, and it means the atom is electrically neutral. However, we know that electrons can move, and when they do so, it creates an imbalance of charge, causing static electricity. Static electricity, I'm sure all of us have experienced this at one time or another. It's a charge imbalance that results in the buildup of excess electric charge on an object. So when objects with loosely held electrons build up on the surface. So a lot of us have probably experienced this if you kind of sashay across the floor in socks and you're on a carpet, and then you go and you touch your brother and your sister or one of your parents, you kind of shock them. That is thanks to static electricity. So this shock that you experience is when that charge is neutralized. So you're discharging that buildup of electrons, that negative energy is being discharged. And so that's kind of what creates that static shock. All right, the rules of charge. Opposite charges attract and like charges repel. So if you have two things that have a negative charge and you try to force them together, they will be pushed apart. If you have something that is positively charged and negatively charged, they will be drawn to one another. The law of conservation of charge. Charge cannot be created or destroyed, only transferred, and net electric charge is always constant. So we're seeing a theme. All of these laws of conservation of energy and law of conservation of matter, basically things are not being created or destroyed, they are just changing forms, and the same is true for charge. Electric field. So the electric field is the area surrounding charged particles or objects within which a force can be exerted on other charged particles or objects. This allows charges to act at a distance. So in this example, the balloon is carrying a charge. So let's say the balloon, we rubbed it on our pant leg or we rubbed it with a cloth, it's going to develop a charge. If you then held that balloon on top of, if you laid out some really small scraps of paper on a table and you held that balloon, those scraps of paper would be, looks like they're being drawn up inside the balloon. The reason for that is because the balloon has that electric field around it. The field can move the charges around an object near it. So it's basically acting on the charges of the paper, and those things are attracting to one another. Charged particles placed in the electric field will be pushed or pulled by the force exerted by the field. How do we detect charge? We detect charge with something called an electroscope. This is a tool used to detect the presence and magnitude of an electric charge. If we were in class, I could have done a really cool demonstration for you, but if you Google or you YouTube electroscopes, you probably can pull up a lot of different videos that will show you. So if you're curious about that, I encourage you to do a little bit more on your own looking that up. All right, different kinds of materials. So some materials transfer electric charge well, and others do not. A conductor, so something that conducts electricity well. Materials that allow electrons to flow easily. They readily conduct electric charge. These are metals. We remember from our study of chemistry that we talked about how metals are good conductors. That's part of what makes a metal a metal. A particularly good conductor that is often used in wires is copper. You know, most of the wires and the electrical in your house employ copper because it's an excellent conductor. Your skin is also a really good conductor, and that is why, when going back to our example of walking on the rug in your socks, if you're walking along the rug in your socks and you're picking up that charge and then you go to touch somebody else, it's because your skin is a good conductor that that charge is transferred to that person and creates that static shock. On the other hand, we have insulators. So when something is, we think of insulation, we think of like a cooler that's made out of styrofoam. It keeps our drinks cold. Well, an insulator are materials that block the flow of electrons through them. So they are not going to conduct electricity well. Examples are plastic, wood, air, rubber, and glass. All of those things are safe materials to have around electricity. They are not going to conduct electricity well. So if you think about the way a wire is made up, so if I were to take the power cord for my laptop and cut it open, you would see that the outside has rubber or plastic, and the inside of it would be wire. So the inside of wires is metal, and that can conduct the flow of electric charge, whereas the outside is rubber or plastic to insulate us from being shocked by the charge. So obviously it wouldn't work very well if we didn't have this rubber coating, because we would get shocked by the wire. But because it's covered with this insulator, which is, I'm not sure whether this is actually rubber, plastic, or a synthetic composite of some kind, but this is what's keeping me from being shocked from this being plugged into the wall. All right, transfer of charge. We can transfer charge 3 ways. The first one is conduction. And so that's a transfer of electrons through direct contact between objects. So if you have something that is charged and you come in physical contact with something else that is charged, the electrons from one object are going to move to the other object. The object must be a conductor to transfer the charge. So if the rod in the picture above was made of, say, glass or plastic, we would not expect there to be conduction, because it is not a good conductor. That's not somewhere where the electrons want to flow, and so we're not going to be able to force that to conduct those electrons. So if it was made of metal, that would be good. Or again, if you took your finger and touched it to that globe, if it had a charge, because your skin is a good conductor, that would allow those electrons to flow. We can also use friction. So if you take a balloon and again, and you rub it on your hair, you rub it on your leg, that transfer electrons by rubbing the object, we call that friction. Socks rubbing on the carpet is another example, and then you touch your sibling and you shock them. That is from the friction transfer of charge. And then the third one is induction, and this one is really cool. So this is transfer of electrons through electric fields working over a distance. So you're not actually physically touching those two objects together, but the electrons are being transferred regardless. So if you bring a charged object near a neutral object, you cause something called polarization, and it induces a charge on the neutral object. So what in the world do we mean by this? Okay, so if this object here, this metal rod, has a negative charge, and this sphere in its neutral state has no charge, when you start to bring this metal rod towards the sphere, because the negative charge here and the negative charge that is naturally occurring in this sphere are like, they don't want to be close to each other, and so they want to repel. So this negatively charged rod is actually going to force the negative charge, or excuse me, the electrons in this sphere away from where the rod is approaching. And so because all of the negative charges, those electrons, are moving this way, that leaves over these positive charges on this side. So basically the electrons are getting as far away from these electrons as they can, and so that is forcing those positive charges to come here. So we know that opposites attract in terms of charge. So what do we think might happen between those two things? That's going to cause something called static discharge. All right, static discharge is the sudden flow of electric charge between two charged objects due to a buildup of static electricity. So prime example of this is lightning. Oops, I already learned, can't go back. Okay, so let's talk about how does lightning work. It's one of the best examples of static discharge. In your summative assessment, you'll actually see some examples of a sort of artificial lightning. But so how do we get lightning? So the movement of clouds and air currents causes a buildup of static electricity in the clouds. So believe it or not, the clouds in the atmosphere, air currents, and the interaction of the molecules create static, much like rubbing our feet with socks on them on a carpet. So when those things are moving past each other and sliding past each other, they're actually causing static, which to me, I think that's really funny to think about, that clouds are getting staticky, but this is how it starts. So they build up that static in the clouds. Okay, so when the electron buildup becomes great enough, a positive charge is induced on Earth. So just like we talked about in the last example with the metal rod and the sphere. So these clouds, let me get my little pointer out here. Okay, so these clouds, they're rubbing back and forth and they're creating this friction. And so these negative charges start to develop on the underside of the cloud. And so these negative charges are starting to repel the electrons, those negative charges on Earth. So those negative charges in the tree and the negative charges in the house are being forced away. As a result of that, these positive charges are moving this way. So we're pushing all of the negative charge down, we're moving all of the positive charge up. But so now we've got negative charge up here and positive charge here. What do we think is going to happen? Eventually the attraction gets so great that the electrons travel from the clouds down to Earth because it wants so badly to neutralize that charge. So we've talked all year about how atoms aren't happy when they're unbalanced. Charges in the atmosphere and in the world in general are the same way. They don't like to be unbalanced, and so they're going to do whatever they can to neutralize that. And so that instant jump of electrons to neutralize this positive charge is what causes that clap of lightning. And so it's really pretty cool. So what can we do to remove charge? So obviously, if this is the way that lightning works, we don't really want that discharging in our house. That could fry all of our electronics. It could also cause injury. And so what we do is when houses are built, they have what's called a grounding rod. And so you've probably heard the word ground before, like, oh, is this, electronic grounded? Some of the plugs in your house have grounding wires. That's what that third little prong is on the bottom. And so the way that that works is the process of removing excess charge on an object by transferring electrons to another object to neutralize the electrical imbalance. So basically, when a house is built, or hopefully when a house is built, they bury in the ground something called the grounding rod. And that grounding rod has a wire lead that goes all the way up through the house and all the way to somewhere on the roof or wherever the highest point of the house is, and to something called a lightning rod. Now, sometimes they're not so big that you can notice. Not all houses have this, and some have it in different forms. But typically, somewhere in the electrical wiring of your house, there is a lightning rod that has a wire that travels all the way down the side of the house into the ground. And so that is so that, God forbid, electricity, or in the form of lightning, were to strike the house, instead of going through the house and frying all of your electronics, it's going to get down into the ground here. The whole process itself is a little bit more complicated than that, but that's kind of the 30-second theater version that we're going to go through for the purpose of this. So it redirects that charge to the ground rather than the building. The second thing we're going to talk about is current. So current. Electric current is the net movement of electric charge in a single direction. And just to take a pause for a minute, this picture is just stunning to me. It is measured in amperes, or amps, and I'm sure you've heard people talk about how many amps something has, and so that's how many electrons are moving in a single direction at any given time. How do the electrons move? So they do not move nicely, so to speak. They don't buddy up and line up really neatly, single file down the hallway. They bounce like a bunch of bouncy balls thrown down a staircase. So if you could fill a laundry bin with a bunch of bouncy balls, and you stood at the top of the stairs and you dumped the laundry basket, and the balls were jumping around and bouncing around all over everything, that's how electrons move. Now, we talked about amps, and sometimes this gets confused with voltage. So voltage difference, voltage is the push. Now remember, we talked about forces, and so it's the force that causes the charge to move. And so it's the force that causes electrons to move from an area of high electron concentration to an area of low electron concentration. So we talked about how heat, for example, moves from an area of high heat to low heat. Well, electrons like to move the same way. We measure this in volts, and charge flows, as we just said, from high voltage areas to low voltage areas. So a high voltage area is an area where there are a lot of electrons. A low voltage area is an area that there are few. And so the voltage is the rate at which these are being pushed. And you can kind of think of it like sliding down a slide. If you slide down a slide, it's going to have a certain speed that you're going to do that. But if you then pile all three of your siblings in your lap and you slide down the slide, you're going to move more quickly. So the extent to which there are more electrons in the area of high voltage, it's going to move faster to the area of low voltage if there are more to begin with. The larger the difference, the greater the current. Circuits. A circuit is a closed path an electric current flows through. And I know that I'm moving through this really, really quickly. Again, I'm just trying to give you guys a little taste of what we would have gone through, just so that if you come in contact with it again, you're like, oh, okay, I remember that. Obviously you're not going to be tested on that. I tested on this. I already kind of mentioned that, but so feel free to pause the video if there's something that you want to learn more about. Either throw me a comment on one of the forums, or feel free. There's tons of Google videos about this stuff on YouTube and all of that good stuff. So sorry that we're moving so quick, but it just kind of is what it is. So circuit, closed path and electric current flows through, it is necessary in order for electric charge to move. If a circuit is not closed, electric current will not move. So in this first picture, we have a circuit with a switch. If the switch is open, current will not flow. So because current in this picture is not flowing, the light bulb is not illuminated. In this second picture, which you probably are having trouble seeing because my fat squash is in the way, but in this picture, the switch is closed, and so therefore the light bulb is illuminated because the switch is closed, it's forming a closed circuit and that electricity is moving. And so does anybody know, we know that this is a switch, we know that, or most people probably can figure out that this part is a light bulb, but what is this? That is the battery. And so batteries are actually really neat. And when I first learned how a battery worked, I was like, wow, all of that is going on in that little package. And so we know that batteries in the house, they have a positive end and they have a negative end. But what do those labels really mean and why are they there? So a battery is a device that converts chemical energy to electrical energy. And so our last unit, we talked about energy transformations and how things can move from one kind of energy to another. So there are a bunch of little chemical reactions that are going on in this battery at all times. They provide a voltage difference between the positive end and the negative terminal of the battery. So remember, we just learned that voltage is that force that's pushing the electrons. And so it's going to go from an area of high electron concentration to an area of lower electron concentration. So it's going to start at the negative end and it's going to push through to the positive end. So when the terminals are connected, so that means when you put this in your remote or any other device that takes a battery, you know that there's usually, in whatever it is that you're putting it, there's going to be two metal ends that this either, clips into, or sometimes if this is in a base with another battery, sometimes there's claw clips. And again, I'm heartbroken that we can't be in the classroom because we have all of the supplies to do some really cool experiments with this. But so when those terminals are connected, an electrical current pushes through the conductor wire because of the voltage difference. So because there are more electrons at this end of the battery, thanks to those chemical reactions that are going on inside, than the positive end of the battery, the electrons are constantly moving this way. And because they are constantly moving this way, it's almost like a pump that's pumping those electrons and it's causing that current to go through. Again, remember that this will not work if the circuit is not closed. So if one of the wires is not connected, or for example, if you ever have an electronic device that you accidentally leave a battery in and maybe one of the ends gets corroded, and it's kind of, it creates an artificial insulator, so that corrosion on the end. And so then maybe you put the battery in and you go to use the remote or whatever the device is and it doesn't work. That's because there's not a closed circuit. So it's, even though it's pumping those electrons, there's nowhere for them to go. And so therefore that circuit's not going, the electricity is not moving, and whatever it is that you have won't work. And just finally, again, the electrons flow from the negative end to the positive end. So negative to positive, more electrons on this end than this end, because of the chemical reaction that's going on. Okay, the very last thing that we are going to talk about, and again, because of the nature of distance learning, you get to skip all the math. Yay! Resistance is denoted by the capital letter R, or as we would say in Boston, the A. The tendency of a material to oppose the flow of electrons through it. So not all conductors are created equal. So we remember that we talked about how electrons they're moving all crazy like this. Well, there's certain factors that make them move less easily than others. We measure resistance in ohms. So it's affected by 4 factors. The first one is, what kind of material are we going through? Insulators have more resistance than conductors. Things that are better conductors are going to resist the passage of electrons less. So things that are better conductors, electrons are going to move more quickly. The size of the wire. So think about this. If you were to dump a laundry basket full of bouncing balls down a staircase, are they going to move better through a larger staircase or through a really small staircase? They're going to move better through a larger staircase, a larger diameter staircase. So similarly, the wire, if the wire is bigger, the electrons are going to move more freely. If the wire is smaller, they're not going to move as well. The length of the wire. This one kind of seems like common sense. If you have a staircase that is 50 feet long, it's going to take longer for the electrons to flow than if you had a staircase that was 3 feet long. So longer wire has more resistance. And then finally, the temperature of the wire. And this one you have to think about a little bit. Remember in our study of kinetic energy, we learned that When you heat something up, what happens to the molecules? They move faster. And so just like that, electrons in a hotter wire, in addition to already being bouncing crazy, they're going to go even more crazy because it's heated, because they follow that same rule that when something is hot, those particles are going to move faster, and the subatomic particles like electrons are also going to move faster. So the higher the temperature, it has more resistance. This is why it is so important that certain electronics be kept at a certain temperature. That's why there's fans on different kinds of electronic devices, or sometimes if there's banks and banks of electronic devices, the rooms are actually refrigerated so that those devices do not overheat and so that electricity can move. All right.